Hello again. This is part 3 of the AP Physics Circular Motion and Gravity Practice Problem Review. We'll be looking at this problem now, which is problem 6 in your packet. At the surface of a planet with radius r, a mass experiences a gravitational acceleration g. And this is a different g than 9.8 meters per second squared. At a height of 3r above the surface of a planet, the gravitational acceleration is something. So now they're saying this object that when it's sitting at the surface, so if we draw the surface of the planet, surface of the planet, and then it has some radius r here. So from the center of the planet, you have this radius. Now they're saying the object is 3 times that radius. Maybe I could draw this better. Above the planet, 3 times that radius above the planet. 1, 2, 3. So that's its height. It's got 3 r's above the surface of the planet. How will the force of gravity change? They told us the force of gravity, which is given by Newton's, we can find using Newton's second law, but they give it to us. And Newton's second law is just gravitational constant g, which is a number that's always given. It stays the same. It's 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. And that's a number you don't need to memorize. It will be given. It's provided on an AP equation table. They give us that as just this variable g. What's going to happen to this if we move that object? So that's the force of gravity when the object is here. What's going to happen to that force when we move it up here? Well, the difference between here and here, the masses don't change. This doesn't change. The distance changes. And instead of r being the separation between the center and the object, now you have 1, 2, 3, 4r. So 4r. So now this variable is now 4r. Remember that anything that goes in place of this r in this equation changes the force of gravity by the square of the inverse of that number. So if we change this r to 4r, ultimately that's going to change the force of gravity by something that's different. It's not going to quadruple it, and it's not going to make it go down by 4 either. What happens is if we substitute, so now this new force is g, same masses, so we'll leave those the same, 4r squared. This 4 gets squared, and you're left with a factor of 1/16. And we could pull that out of the rest of this expression. And this should look familiar. This is just what we call g. This equals g. So this new force is just 1/16 of the original force, so 1/16 g. And if we look at the options that are given, we see E is the right answer. Now we can look at the next problem, and it's problem 7 in your packet. It involves a motorcycle rider, and he or she is attempting to complete a loop with a diameter of 10 meters. If the mass of the motorcycle is 200 kilograms and the mass of the rider is 85 kilograms, what is the speed of the bike at the highest point? If a sensor measures a normal force on the bike and passenger of 560 newtons in meters per second. So we're given this 560 newtons as the normal force at the top of the loop. So to help me understand this problem, I'm going to draw a picture. There's this loop, the motorcycle rider, I'm just going to draw as a box. Well, go in there a little. And ultimately, we want to know the speed of the bike at the highest point, so at this point. And what we know is the mass of the motorcyclist, 200 kilograms. And the mass of the motorcycle is 85. So I'm actually going to add those because I feel that the system itself, the forces are all acting on the motorcycle and the cyclist, the motorcyclist. So I'm going to list their combined mass as 285. We also know that the loop has a radius of 10 meters. And at this point, there's a normal force. So remember, the normal force acts between the surface and the object. And it's always perpendicular to the surface, so maybe that's not even a good way to draw it, but if this is a circle and this is the center of the circle, then the normal force is just going straight towards the center of the circle. And that normal force is 560 newtons. What other forces are acting on this object? What is the force of gravity? And that is equal to the mass times acceleration of gravity on Earth. And there might be a force of friction, but it's not mentioned in the problem, so we're going to assume that it doesn't exist because we're not given any information about friction. We want the speed, and that's pretty much all we know. Let me double check. Oh, the diameter is 10 meters. Pardon me. So this is actually the diameter, which means the radius is 5 meters. Good thing I went back and reread. All right, so if I look at the system, which is this motorcycle, passenger, and surface system, the forces acting on the bike with the passenger are just the force of gravity and that normal force. And the bike is moving in a circle, so the sum of those forces, the net force, is a centripetal force. So it's going to have a centripetal acceleration. Anytime an object's moving in a circle, we can say that it's accelerating centripetally due to its net force, and centripetal acceleration is always pointing inward. So even just looking at this picture, the sum of the forces, if we were to put these two vectors tip to tail, then they would add up and still be pointing towards the center of the circle. So these two are going in the same direction. I'm going to say this is my positive direction, just to keep things consistent. This force of gravity is mass times 9.8, and the mass, the combined mass of the bike, is 285 times 9.8, plus the normal force, which is given as 560. And that's all equal to the mass of the object that's going around a circle, so it's 285. Velocity we're looking for, and the radius. So this is, remember, this radius here, when we're looking at centripetal acceleration, is the distance from that the object, the distance between the object and the center of the circle. In this case, it's 5 meters. So putting that into my calculator, 285 times 9.8, the force of gravity on the bike is 2793 plus 560. And that equals 3353 newtons. On this side, we have that 285 over 5 is just 57 v squared. At this point, I can solve for v. and it's just going to be the square root of 353, or 3,353, divided by 57. That number is 58.8, and then square root of that gives me 7.66, or 7.7. And the units are meters per second. So that's our final answer. The answer is D. Next problem. If the velocity of a motorcycle rider is the same at when it reaches the bottom of the loop, what will the normal force be on both the motorcycle rider if the loop? What will the normal force be on both the motorcycle and the rider if another loop is attempted? Both objects are still in circular motion in the loop. And they want the answer in newtons. Oh, yeah. So at the bottom of the loop, they're saying the force, we use the same velocity, then what will the normal force have to be? Now if we were to draw the free body diagram, normal force and force of gravity are opposing each other. So if the motorcycle rider's here, force of gravity is this way, and normal force is that way. Now the sum of forces, which is equal to ma, and it's accelerating centripetally, so we can plug in centripetal acceleration. Let's keep that as, so if we keep that as our positive, we have to be careful, because then we have to think about what direction it makes this side. Let's not forget that Newton's second law tells us a relationship between vectors, not just scalars. And vectors are anything with magnitude and direction. So really, this F is a vector. The sum of forces are all vectors, and in this expression, this side, you have that acceleration as a vector. So if we're setting this to be our positive, like last time, then now our acceleration, our net acceleration, is actually pointing inward. And according to this coordinate system, and according to the way we labeled these forces, this normal force should be bigger, should be much bigger than the force of gravity. And so the net force, when you add these two up, should give you an arrow pointing inward, and that would correspond to the negative direction according to our coordinate system. So I'm going to make sure I set that side to be negative. And the sum of forces acting on this object, much like last time, are just the normal force and the force of gravity. And in this case, normal force is also in the negative direction, same direction as the centripetal, the net force. So the direction that object is accelerating towards is the center of the circle. The normal force is what we're trying to find. So I'm going to rewrite normal force in terms of what I do know. So this negative mv squared over r minus the force of gravity. When I plug in all these numbers and change the negatives to positive, I get that the normal force is about 6,172, which rounds to 6,200 newtons. So I just want to summarize really quickly that the story this equation, this setup is telling us that if you have something moving in a circle, that's what this side is saying, then the only things acting on it are normal force and the force of gravity. And we set it up in a way where we decide how fast it's going, and we set it up this way so we can find out what the normal force is required